Hi friends, welcome to my channel. Let's have a look at a newly appeared problem. Problem 2638. Count the number of key-free subsets. In this video, we want to explain how to reduce the problem into some smaller problems and then solve the problem by solving the smaller ingredients. So first, we are given an integer array called nums, which contains distinct elements and an integer key. A subset is called key-free subset if it contains no two elements with an absolute difference equal to key. Notice that the empty set is a key-free subset. So we are required to return the number of key-free subsets of nums. So a subset of an array is a selection of elements. So here possibly none of the array. So there are 2 points to be noticed here. First, the array nums contains distinct elements. So in effect, we can regard this nums array as a set in a mathematical sense. Secondly, the empty set is regarded as a key-free subset. Therefore, we need to include it when we do the counting. So we are required to return the number of key-free subsets of nums. So that's the requirement. There are 3 examples given. So the example 3 is very special. The reason is that so for any 2 elements in this nums list, so their difference cannot be 20. Therefore, any subset of this nums will be a key-free subset. But as a set, there are 4 elements, so their power set has 16 subsets. The 16 is nothing but 2 to the power 4, right? So this is example 3. So example 1, so if you regarded this element in a sorted order, that is 4, 5, 6, so their difference is 1. So the output is 5, right? So please keep this in mind. So we're going to come back to this part. So example 2 is sort of the general scenario, right? So actually we can have 3, 8, and 2, 5. These 3 groups. So the output is 12. So we're going to interpret this after we finish the coding. So before we move forward to the coding, let's also look at the constraints. So this constraint actually can contain very crucial information. For example, in this problem, the first constraint is very important, which basically says that the length of this nums list is not very large, right? So the second and the third constraints basically said that the elements in the list and the key itself are all bounded in between 1 and 1000. So with that said, we are ready to do the coding. Let's first explain our plan, right? So here our treatment is problem reduction. So basically we reduce the problem into ingredients, into smaller parts. And then we solve the smaller parts, hence solving the problem itself. So the plan will be the following. First, we are going to decompose or slice the nums as a set into arithmetic sequences with difference key, right? This is the first step. And then for each arithmetic sequence, we compute the number of key-free, right, subsets, and then we just apply a multiplication, right? Multiplication rule, right, or product rule. So this then partially following the hints, right? 1, 2, 3. Yeah, but if you have some background in mathematics, so this procedure will be very straightforward, right? So here we are going to write two utility functions serving the first and the second item in the plan. The reason we wrote this, we are going to write this function is that we are not targeting for solving this specific problem, but we want to solving a class of problems. So with that said, let's look at the coding part. So first, I'm going to write a slice the nums as a set into arithmetic sequences. So we are going to use a utility function. So this function will continuously call this utility function. So here let's do it called select. So we have a start, so which is an integer, and we have a diff, so this is difference, so it's another integer. So right, so we have a set, so we're going to use an integer, and a set, so we're going to use a set, and the return type will be a list of integer, right? So if you do not want to include this type hints, you just delete them. So for this purpose, let me first initialize an empty list. Then we're going to select with a start, right? So basically for y in this sequence, that is range. So we have a start, and then we have the start and ending point will be start plus let's undo diff times. So here I'm going to use sets plus 1 to make sure. So we have sets and number of elements. Then the difference or step will be diff, right? Then what we're going to do is to check if y in S and so either the result is empty, or so y minus diff equals the result -1. So in other words, they can form a chain, right? And then we're going to append this y to result, and then at the same time we are going to update the set. So we're going to remove y from S. Otherwise, we just break. And we want to return the result, the list itself, also the current state of S. So this is the utility function we're going to use. So you may ask how to use it. So here is how we use it. So let's initialize a empty list. So this aux will hold the arithmetic sequences sliced from the nums list or the set. So first I'm going to make it a set. So here we are doing a type conversion, and then we are going to use a while loop. While S is not empty, we can do the slicing. So what we're going to do is basically we select. So we start from the minimum element from S, and then we want the slice to be k in this problem, and the length will be, so let's write list plus S, so or larger one. It does not matter because we have this check y in S. And then the set we are going to slicing from or selecting from will be S. Then we're going to have a temp, this is the list, and also we're going to have a new state of S. So here we're retrieving the temp and updating the state of S in one go, in one sentence. Then once this is the case, as long as S is not empty, temp will be not empty. Then we can do aux append temp. So that's it on this step. So basically you can print out this aux. So here let's print out this. I'm going to write a return just to confine with return, but the purpose is to test the utility function. Let's do a check. So in this one, it just returns 1 as expected. For this one, it's going to replace to return 3, right? So you can check that. So 1 is 2, right? Because 2 plus 5 is 7. 7 is not inside, right? So we stop there. Then we have 3 and 8. Their difference 5, and we have 5, right? So now we are ready to interpret this example 2. Because for one element set, so there are 2 key-free subsets. One is the empty set itself. One is a single element. So we have 2 here. So for 2 elements set, so we have empty set, we have two single element subsets, that is 3 and 8, but we cannot have the 3 and 8, the two element set, because they are not key free. So in this case, and this single arithmetic sequence contributes to the result by 3. So this is another single element set. So this is 2, this is 3, and this is 2. So 2 times 3 times 2 will be 12. That's the output in example 2, right? So now we want also to interpret example 1. So now let's look at the second part. So the second part, let's call it step 1. That is find for each arithmetic sequence above the number of key-free subsets, right? For this, actually, this is just some simple counting. So we can use dp here. So here I'm going to write some verbose dp just to demonstrate to you the finer detail. So let's define count key-free. So accepting the array from above, right? And then what we're going to do, first let's track the length of this array, right? So we can assume array is not empty, right? If it's empty, it's just return 1. So if n equals 1, so it's one element array. So the number of key-free subsets is 2. If n equals 2, so as we explained, it's 3, right? So now let's look at generic case. So in this case, we're going to use a dp table. So for this, and then we're going to interpret dpi. It will be the number of key-free subsets that can be constructed from this array up to index I. So we write I plus 1 here, right? So don't forget to make some initialization. For example, dp0 corresponding to 1 element, that is 2. dp1 corresponding to 2 elements, that's 3. And then we're going to iterate for I in range 2 up to n minus 1, right? So we can do this, right? So if we choose the current element at index I, so we cannot choose the element at index I minus 1. So the contribution will be I minus 2, right? And then if we do not choose the element at index I, then we can choose the element at index I minus 1. So the contribution is dp I minus 1. Then we just need to return dp negative 1, right? So now we can interpret example 1. So here let's print count key-free. So let's use this 4, 5, 6. We assume that the key will be 1, right? So here's 6, right? So we have right. So now let's still return a 0 just to confine to the constraint of return type. So this should give us 5, right? So this is 5 as expected. So now let's continue the coding part, so which is almost done, right? So we just general case for the problem. So we have already generated this arithmetic sequences. So we just need to apply or map this function to the elements here, right? And then we do the multiplication rule. So we initialize a result by 1, and then for array in aux. So basically, we apply this function to array, and then we multiply the result by this factor, and finally we do the return, right? So this is the full solution format to this problem. So now let's do a check first. Yeah, it passes a test case. So now let's look at the generic case. Yeah, it passes all the cases. So actually, in my first try, we write the correct solution, and then in my second and third try, I rewrite, but I forgot to use initialization here, so which leads to wrong answer. But now that's just some set detail. So here, let me give a quick summary for this video. So in this video, basically our purpose is to demonstrate how to reduce the problem into smaller problems, and then solving the problem by solving the smaller problems. So in between, so basically we use the 3 steps. So in these 3 steps, step 0 and step 1 are basically 2 utility functions of general purpose. And then the last step basically is accounting, right? So here we wrote the code from scratch to demonstrate the finer details. But there are some Python built-in functions which can make the code shorter. For example, here, right, we can use reduce and we can use map, right? But that's not our purpose. So our purpose is to demonstrate the use of problem reduction and demonstrate the 2 utility functions. With that said, basically that's about it for this video. If you found the explanation here of use, you're welcome to follow me in YouTube channel. With that said, thank you.